D of 0, 0, according to that definition, can you imagine what that is? D of 0, 0 is a set of all common divisors that divide 0 and 0. Everything is written Z, right? Everything is all integers, right? But as long as this is something else, like they're saying, and it's going to be finite set and small set. Make sense? Good. So D of 0, 0 does not have highest number, right? But everything else, it has largest number. And that is called greatest common divisor, GCD. Question? All right. I have my calculator right here. I'm ready. Okay, let's go ahead and do this. Go ahead and find this set. Set, right? How many elements does this set have? Well, my answer was finite. That's what answer I was looking for. But you're right. You're right. I don't know. That is the correct answer. Or it exists, something like that. Right? Well, let's compute that. Once you have one number, you always have a negative number in there too, right? Yeah. 361, 289. Compute the set. How many elements does it have after you list them down? You need a calculator. I'll allow you to use your phone just for this moment, but next time you can bring one. The reason I'm setting this one out is what is your natural approach to this very first concept you did, right? You're going to do something, right? Yeah. Factorization, right. Yeah. That's right. That's why I chose this guy, because you don't see it immediately. So you have to do a little bit of scratch work. Not a little number. No. Yeah. Without calculator, you'll just, I don't care kind of attitude. I didn't silence my phone. Oh, 17 was it. Was it 17? 17 goes where? 289? 289 is 17, I think. 17 goes in there. 17 squared. Bingo, he found it. Took 2 minutes. All right. 19 squared. Oh, he said it. 19 squared. There it is. Yeah. All right. So you look at each of the number and think about which one, what divides that, and then our answer is a D361 question. Answer? Plus minus 1. Thank you. And what else? 0 doesn't divide anything. Yeah. So one way to find an answer is to say it, and you immediately know, oh, it is right or wrong. That's it, right? That's it. Okay. Thank you. Two elements. Yeah, two elements. All right. What is a GCD? They also write it like this: GCD of 361 and 289. Largest one is 1, right? So GCD of this thing is 1. Fair enough. That's it. That's our definition. That's just at this point is a reasonable approach. This is really important part. What was so important? Long division, right? Seems like important thing, right? We spend a lot of time on that. This is like really, really important. It is the most hottest application of long division, right? This is really cool application. Here's my take. This will allow you to calculate GCD in amazing way. And here's an expression for that. If you use that method you just did, if it takes n hours, all right, this method will take that time down to log n hours. Sounds good? I'm going to show you some result. If this method going for factorization and what divides, that takes n hours, this algorithm that takes it down to log n hours. Suppose there are a group of people about to discover the beauty of mathematics and did not know this Euclid's algorithm before that Greek period. They were spending this much of a time. To compare that, I calculated this. No, I didn't calculate that. It's here. I ran it a little bit with just sample exponential functions here. Right. So opposite, you go and create this pair of two numbers. They're so long. To apply this algorithm to find the GCD, it take 15 hours. Right? Pentagon created this 3,000 digit long number, two of them, and you run this Euclidean algorithm to find what the GCD is. It took 15 hours. The other guys, not knowing this algorithm, takes 3 years. That's it. All right, let's push it a little further. Let's go up to 2 more hours. Why not? Crank the machine, make the number such that Euclidean algorithm takes 17 hours. The other guys, not knowing the secret, 14 years. The same computer, crank it, it takes 14 years. And Pentagon goes, oh, we only know this one. It's pretty much safe. We're safe for down to 14 years. Use that. And that's how the crypto system is based on. Unfortunately, everybody knows this thing, right? So we can use that. So, but it just gives you some idea. The stark difference between what you just did, factoring, versus what we're about to learn. There's a 17 hours versus 14 years. That is the time we're looking at right here, right? And then later you're going to learn, no one knows how to redo that. One part, when you're executing, it takes this much of time. Undoing takes this much of the time. And no one knows how to break that. Because of that, if you just crank this one for 17 hours, you're safe for 14 years, next down to 14 years. That's how the crypto system works. If quantum computers developed, all this thing changes. But right now, in mathematicians' understanding, this is still standing, and you will see some of the examples. All right? But this kind of gives you that stark difference of computing time, what you just did versus what we're about to learn. Okay? What is it called? Euclid's algorithm, Euclidean algorithm. And this lemma, I'm going to call this lemma of Euclidean algorithm. The book only has this one. After thought about it a little bit, it's really nice to have this statement. This is a much better statement. Think about it. If you can show A is QB plus BR, common divisor set of A and B is equal to the common divisor of B and R, then of course the largest common divisor here is the largest common divisor there, right? This follows trivially from that statement, correct? So, and you go through this in the proof anyway, so why don't we state it as a statement like that and abide by it? Okay, ready? Exercise 2. You prove this statement right there. It's exercise 2. Exercise 1 was that thing that you didn't do because you don't have a calculator. Yeah. Yeah. It is so simple. And after you finish this proof, wow, this is so simple. And then you go back in and here, why does it make such big difference? So I proved one direction. You can check with me, and I chose an arbitrary element from DAB, any common divisor of A and B, and I concluded that D is also divisor, D divides B and D divides R, therefore it's a common divisor B and R as well. There was actually lemmas and things like that, so you could have used that, but this will be some self-contained proof. But there were theorems and lemmas that you could conclude it from. All right. So see if you can do backwards. How was it? Was that okay? So simple, right? Just this device and that device. Just simple. Yeah, but if you go back and this your first idea of going for a common divisor and this one makes this much of a difference. 17 hours versus 14 years. Jesus. But it's this idea. And people are out there looking for this all the time. Oh, these fancy mathematicians, they're saying, oh, they know much. You can't do that. You just want to come up with just simple attack like this. It breaks the entire ground, something like that. So people are always out there try to break that barrier. Called hackers. All right. Any question? All right. You actually have to learn the algorithm. This is just a lemma of an algorithm. So what just happened here is that you started with A and B. That's large size number, right? Then you can switch to B and R. What's good about R? R is smaller than B because it's a remainder, right? It doesn't say here's a remainder. That's another interesting thing. It doesn't say R is a remainder, right? It didn't put that condition in there, but it allows it to be that, and then you can use a smaller size, right? Then do you see that you can repeat that again? B is bigger than R, right? Divide B by R again, knock down again, knock down again, and that was the algorithm. So I'm going to give you this abstract description because I think it's simple. I think you can apply that to actual specific case, not Here's the specific algorithm. You learn an algorithm. Then you understand abstract statement. I'm going backwards sometimes because I believe you can do that. All right? Okay, here's the abstract statement. Here's an algorithm. What is the name of this algorithm? Euclidean algorithm. You start from A and B, right? Now it's replaced by Bn R. That's first remainder R1 there. All right? Is that okay? Also, I want you to have, you are actually thinking about, you are actually doing this one. Here's A bigger, B smaller, you divide it, and you have a remainder, right? Also, it's going to be beneficial to record the quotient underneath it. You write R1 there, record the quotient underneath it. You have to go through the quotient anyway, right? When you're getting this R1, it's right in front of you. Why not? Record it. All right? What is the next one you think we're doing? We're going to divide what by what? Right, B by R1. R1 is smaller now, right? Smaller than B1. So you get new remainder, right? So you're going to replace, it's B and B adjacent and R1 adjacent. Now you have a new remainder, right? And then you have a new quotient as you divide B by R1. Good? And then you do that again and again until you reach something like this, right? But isn't this number always going down? B is greater than R1 or R1 is less than B? R2 is less than R1, right? Rn minus 1 is less than Rn minus 2. These numbers keep going down, right? You cannot do that forever. Integers, right? You start with 5,000. Eventually, you have to stop. How is it going to stop? Yeah, that's the only way it stopped. So this is, the last bit in here, Rn there. And if you do that, if you divide that, you get 0 in there. I think they call that 0 there. I think that's right. I think that's what they do. All right. Make sense? All right. So you record this last one into Qn minus 1. Let's see. That's right. Rn. That's Qn there, right? Okay. Yeah. And when you reach this one in here, think about it. What is the set? It's a divisor of Rn, right? Anything that divides Rn is going to divide 0, right? So don't you think this is precisely the divisors of all Rn, kind of disregarding 0? Is that correct? So what is the GCD of Rn and 0, you think? Rn. Rn is the largest one that divides it, right? As long as it's non-zero. So Rn. So largest divisor is Rn. How about here? What is the largest divisor here? Rn, because these sets are all the same set, right? Uniform method. Fair enough? Yes. Right. So it goes down by, this remainder should be greater than equal to 0, right? But it's always a smaller. But if it goes forever, how is it possible if you have to remain greater than 0 and going down one step at a time, going forever, that must pass to 0, right? But remainder is always in between 0 and B. So it must stop. Interesting, right? That's the idea. And we're going to actually apply this one to actual example. Okay, I'll give you two numbers. Keep dividing and record Rn naturally here. Also record the Q's down there as well. Yes, integers, that's right. No, not necessarily. Yeah. But there's interesting polynomial version as well. Yeah. That's right. Oh, geez, polynomial. All right. There it is. Yeah. Like it. All right. For that one, we're just going to say apply the algorithm. Apply. It's an exercise. What is the number? 3. Exercise 3. Apply the algorithm. Yeah. My algorithm is slightly different from the book. What is different? I use D instead of GCD. And what do you write underneath it? Cues. Record those cues. Yes, we'll use it. Yeah. Yeah. You got my obvious answer. Yeah, go ahead. Hmm. Common divisors, yeah. No, I want you to look at your algorithm starts from A and B. That's A and B, right? You think about, I just copy the B there, so I give you that. You see that? What is R1? It's a remainder of 1492 when divided by 1066. Yeah, that remainder goes there. Yeah, and then repeat that over and over. Yeah, did you get R1? Not yet? Yeah, 1492 divided by 1066. That's right. What's R1? 426. Can somebody give me R Q1 as well? 1, thank you. All right. Someone else get the second one. Let me have it. This is so convenient. 214 sounds familiar. Yes. Quotient 2. Anybody second that? Okay. All right. 214, 212 is quotient 2 this time? Quotient 1. That's right. Hmm. If you do one more time, you get, if you divide it. Yeah, quotient is 16. Yeah. That doesn't go into the D thing. Yeah. All right, we finished the Dr. Chang's version of Euclid's algorithm. Yes? Yeah. He's the one with machine. Yeah. This is R1, remainder, remainder, remainders, right? Remember that part. Mm. Yep. Yeah. Uh-huh. But I like that it's chained like this. 426, 214. That's what I like about this chain. 212 chained together, get the remainder, right? So that is the end of exercise 3, right? It goes 0. That's the magic. Every single time. Isn't that fun? Yeah. You're left with it 0. That's what happens when you go, leave this world. That's what that is. Dying. You're left with this is dying procedure. This is how you die. That's Euclid's algorithm. Down the hole, you got nothing. All right, let me challenge you with one more question. Can you go ahead and write down all the elements in the common divisors of 1492 and 1066? Can you? All the divisors. All the divisors, 1, 4, and 2, and 106, by just staring at it. Yeah. I know 1 plus minus 1 always there. That's the easy one. Plus minus 2. So do you see a few more? Yeah. Plus minus 2 works. But what other things are there? Yeah. Alton is so sure that that's it. How can you explain that this is it? Yeah. That's the same set. Uh, that's right. That's the same set, remember? Yeah. So we stop right there. So can you answer that? GCD? 2. Yeah. My calculator has GCD. Yeah. So if you type it in there, you get answer right away. Yeah. He's been in my calculus course, and I go like, "You get 0 if you do this in my test," kind of thing. All right. All right. Next one is called matrix version of Euclid's algorithm. Ready for that? All right. This is really fun part. This is really fun part. So rather than writing down 1492 and 10066, I'm just going to abbreviate like this, A and B. Is that okay? Write it like this. Turn that into column vector. Who dislikes column vector? I like column vector. This is a wonderful thing. A and B, turn it like this. All right? Now, what is the next number? B, R1. Isn't that right? That's the next number. Turn it into column vector. Put arrow in between. Now, what is the next number? R1 in there, right? And R2. You see that? Go all the way down to how many? 4. So R3, R4. That's this guy here, right? And then we enter R4 and 0 there. Okay? Or if you see the column vector moving around like this, some L word coming to you, column vector changing to another column vector called linear transformation. Yes, linear transformation. So here is your exercise number 4. AB. This is actually actual number. The 4 numbers going in there gives you BR1. Find it. Exercise number 4. The numbers are all up there, right? How do you go from the first set to the second set, which are identical set? There's this information there. Yeah. I think the first row is easy. First row is easy. How do you pick B, right? Can we do first row together? Yeah. What's the upper left corner entry? 0. Someone else. Upper right corner. 1. There you go. That's our, give yourself 1 point. Got half of them, right? So fill in the remaining 2 parts. Then you pick up the other 2 points. You have to write some equation about R1, right? That's the key. What is R1? can I describe R1 in terms of A and B? Then there you go. What is R1 in terms of A and B? Then you know the answer to that. Got it? All right. What is it? 1 and negative Q1. So it's negative 1 here, right? Right. You have R1 is it's negative Q1, right? R1 is um, right. You see that B is A is wait a second. Yeah, yeah, A is BQR1, right? That's right, minus QB. That's why there's negative there. Negative Q1, but Q1 is 1. Yeah, that's right. Yes, you're right, right. So you want to write down. I misunderstood. Q1, right? But Q1 here is 1. That's what we. Fair enough. Okay. All right. Then you got the pattern, right? So I hope you see this thing now. All right. I start from there's a dot dot dot. We repeated this one. We arrive in the following. We start with the AB, multiply what matrix? 0, 1, 1, negative 1. That's a Q1, right? Then look at this whole thing as a column vector. This is B1 R1 column vector, right? You multiply left again what by what matrix? Can somebody go for that? It's always 0, 1, and 1, and this one here is negative 2. Thank you. And here one more, 0, 1, 1, negative 1. One more, 0, 1, 1, negative 1, right? Then you arrive at, if you do that, I think you arrive at 2, 0. Don't you think? To arrive at there, I think I should stop right here. Right, to arrive to the R4 down here, that's what I want. R4 and R3, you multiply 3 of them, I think, to enter that. Multiply that. Fair enough? Okay. The magic is that if you simplify this to 2 by 2 matrix and reveal some secret, very important relationship between about A and B. So go ahead and multiply this one out. That's not exercise. Just multiply just 3 matrices. So another trick I came up with is that when you write down this matrix, when you multiply, write it underneath it like this. When you're actually calculating this. So you multiply this matrix underneath it, then you can multiply right away. So here 2 and here, if there's a third one, write it under here, here like that. And then multiplying all these matrices is actually, you don't have to repeatedly write same thing over and over. So you multiply these two things first, right? Write it underneath it here. Then multiply these two things, write it underneath it there. And that's how you quickly multiply matrices. Okay, so let's do that. Is this right? I think it's right. Right, what's the conclusion? If you do AB and what do you get? R3, and especially what is R4? R4 is 2, right? Replace it there. It reveals the following. 3 times A minus 4 times B is 2, which is the greatest common divisor of A and B, correct? So let's write that. 3 times what was A? 1492, right? Minus 4 times what was B? 1066 is 2. Out of all that, this is all we got. 3 times 142 minus 4 times 160, 1066 reaches the greatest common divisor. All right. This figuring out this number, 3 and 4, that reaches common divisor, seems not easy. Only this algorithm allows you to do that. Okay? And we're going to use that one. And it has a name. It's called the Bezout identity. Apologize that that part was a little bit incorrect. I multiplied 3 matrices, but I had to multiply one more so that you actually arrive there. So that would be the correct multiplication out there. Down there, hope you can see. Maybe I have to raise it a little bit just for this. And if you multiply one more matrix, we enter these entries. And to get to that GCD, we have to use the bottom row. That gives you negative 5 times A, which was 1492. 7 times B, that's 1066. That really gives you that GCD down there. All right. So if you arrive there to get to that matrix, you have to get to that entry there, that coming from that matrix that is coming from that quotient there. Thank you.